In this video, we're going to talk a little bit about exponential growth versus logistic growth. So if you're in a calculus course, you've likely solved the differential equation that yields the exponential growth model. You see that graphed here in blue. If you're in Calculus 2 or Calculus B, AP Calculus BC, you've probably also dealt with the logistic growth curve, which you see here in red. So we'll start this by going through something that I've got another video that all the details are laid out in. But if you assume that the rate of growth of a population is proportional to the current level of the population, you can separate your variables, integrate each side, solve the equation for y, and what you end up with is you end up with this y equals a e to the kt general solution. That is the exponential growth model. Now, the exponential growth model can be used to solve problems like this. So in 2010, population of Earth was about 6.9 billion people. Then in 2020, it had grown to 7.8 billion people. If we assume a continuous growth rate, or assume that the rate of growth is directly proportional to the current level of the population, we want to develop a population growth model and use it to predict the population of Earth during these years. So what I'm going to do is I'm going to let time 0 be 2010. So in 2010, at time 0, I had 6.9 billion people. I plugged the y value in place of the y in that equation from the prior screen, and I plugged 0 in place of the t in that equation from the prior screen, and that gave me my value for a. Now if I plug in this other condition here, after 10 years from 2010, so in 2020, I had 7.8 billion people. I've put 7.8 in place of the y. I've put 10 in place of the t. I also have this value that we identified for a going into it this time around. Doing some algebra to try to isolate k, and I get this solution for k. That's a 10 in the denominator. Don't really know why a little portion of it got erased. So here is my growth model for the population of the planet. And what I would do in order to figure out my estimate for the population in 2025, I would recognize that that is 15 years after the t equals 0 location. And if I put 15 in place of this t and evaluate this, I end up with 8.3 billion people. 2050 is 40 years after 2010, so 40 years after our 0 location. Doing the same thing with 40 as we did with 15 gives me a prediction of 11.3 billion people. And then 2500, that is 490 years after the t equals 0 location. So if I put 490 in place of this t, I end up with this answer right here. Now these units in this column for y are all billions of people. Seems reasonable, 8.3 billion people. 2025, not bad. Getting a little bit higher, 11.3 billion people. 2050, getting kind of big, but still seems feasible. This does not. This is 2,804 billion people. That is almost 3 trillion people. One of the big weaknesses of this exponential growth model is it typically does well over shorter time frames, but it's going to start to lose some validity over longer time frames. If you look at this table right here, these are the projections from the United Nations for the population of Earth at various times. We had 8.3 in 2025. We're a little high, but not too bad, right? We're looking at a little closer to 8.2 billion than 8.3 billion. In 2050, we're now a little bit beyond what they would have projected. And then they didn't go out to 2,500, so I added one more data point here. In 2100, we would have our model predicting 20.8 billion. You see, now we're almost double what the United Nations is predicting for the population of the planet in the year 2100. So again, the weakness to the exponential growth model is it does pretty well at projecting populations over shorter time frames, but it starts to lose validity over longer time frames. And here's why. On this screen, I have in green our exponential growth model that we've been dealing with throughout the past few screens. What I have in black right here is a horizontal line at 16 billion. The maximum sustainable population of Earth, and I got this through the highly scientific method of doing a Google search, is projected by many studies to be 16 billion people. What happens with our exponential growth model, and you can even think about the bigger portion of one of these graphs that we see here in blue, this graph is growing, growing, growing over time, but after a longer time frame, the slope of this graph is getting so big that it's going to start to have the y value growing extremely rapidly. Our model with exponential growth, which is in green, actually starts to move past the projected maximum sustainable population for Earth, as indicated by a Google search, after 70 years beyond 2010. Now, this logistic growth model, and we'll have some more videos that talk about the specifics of this, the logistic growth model, you'll notice it's kind of moving in the same direction as the exponential growth model initially, right? So it's doing that same job as projecting the population of Earth over these shorter time frames. But then what happens is this graph starts to taper off, and it's going to reach that what's called the carrying capacity, or the maximum sustainable population of Earth that's projected to be 16 billion people. It's reaching that ceiling and never going to exceed it. So in the upcoming videos, we're going to talk about the specifics of this logistic growth model. Exponential growth works well at projections over shorter time frames, starts to lose some validity over those longer time frames because of how quickly those exponential growth graphs grow.